discussed. So there are few more problems what we can discuss in this case. So let us discuss one more problem and let us move ahead with the Smith chart for which we'll be using the stub length identification and the other parameters. So in next problem, what they have specified, a 300 ohm line is terminated by an unknown impedance. So this is nothing but this is the ZL value and it is unknown. VSWR, that is voltage standing wave ratio, is 4.48, and the first voltage minima, and the first voltage minima. So this parameter is important for us. It is a voltage minima, and it is the first voltage minima what we are obtaining. So first voltage minima is situated at 6 centimeter from the termination. So what is he specifying? He is specifying that I am having a voltage minima at a distance of 6 centimeter. 6 centimeter from where? 6 centimeter from the load. That is the termination what he is specifying over here. So indirectly, if I just check how it will be, if this is the load impedance, if you traverse a distance of 6 centimeter, you will encounter the first minimum. In this case, you will encounter the first voltage minimum. Then what is the other parameter he is specifying? This happens when the frequency is 200 megahertz. Determine the unknown load impedance if the line is in air. So this is specifying that air, it implies that it is in the vacuum. So therefore phase velocity will be equal to the speed at which the light travels. So why is this given as since they have given 200 megahertz frequency, they have given the two parameters. One is frequency. Therefore, I in this case, I specified that the velocity is equal to c. I can identify what is lambda. Okay, I can identify what is lambda. So that is what they have specified. So here we can see in the first step, we need to identify what is the wavelength. The first step is identify what is the wavelength. The wavelength is 150 centimeter. What are the other parameters he has given in the problem? He has specified that 300 ohm line is terminated. So this is nothing but the characteristic impedance of the line. The load impedance is unknown. I have to identify the load impedance. He has specified the VSWR parameter to be equal to 4.48 and first voltage minima is occurring at 6 centimeter from the termination, that is the load. So these are the parameters what he has specified. So Z0 is 300. See, rho is given by VSWR, which is equal to 4.48. First voltage minima is at a distance of, it is termed as Zmin. The distance is termed as Zmin, which is 6 centimeter from ZL. Frequency parameter specified. VP is given as C. So therefore, lambda is around 150 centimeter. So now, whenever we are utilizing any of the parameters, right, we need to normalize those values. So one is the impedances what they have given. I'll be normalizing using Z0. So if any impedance is there, I'll be dividing it with Z0 and plotting it on the Smith chart if the need be. Then here I am having a length parameter. So this length parameter, I have to normalize it by dividing this parameter by the wavelength. So therefore, what I'll be obtaining in this case, it will be 0.04. Now there are other things to note down in this case. What happens is, now if this is the load end, if this is the load end, what happens is because of the incident and reflected waves, right, there will be a voltage standing wave formed in the transmission line. So because of which, when we measure the voltages along the transmission line, we will encounter multiple minimum voltage points and multiple maximum voltage points. Apart from this, he has specified that from the load end, if I move a distance of 6 centimeter, I'll encounter the first minimum. So voltage minimum is encountered at a distance of 6 centimeter. Now, if I want to go for the next voltage minimum, right, from this, it will be lambda by 2. Distance between two voltage successive voltage minima is actually lambda by 2. So this may be required when you're solving some other problems. So now what is the first thing I have to do? So this is the aspect on which we have to deal with the problem. So first thing is, since VSWR is specified, right, we need to plot the VSWR circle. So what should be the radius of the circle? It should be with respect to the VSWR value. So what is that value? Sorry. So this circle, what they have drawn, this actually corresponds to the VSWR circle, which is equal to 4.48. How this is 4.48? Wait, just use. It is not clearly visible, so I'll just check out. Uh, so here you can see that we have voltage standing wave ratio here also, here also. So here I'll utilize this scale over here. So here you can see that this values what are there, this values. So on whichever chart you have, right, you have to refer to that chart and you have to see where voltage standing wave ratio scale is present. So you have to refer to that and you start off with this center point. You start off from this point and you have to traverse and mark the point 4.48, because in this case they have given that VSWR is 4.48. Now what you have to do is you have to measure the length of this. That is from, say, I'll mark this as point O and this is the VSWR point. So I'll mark it as point A. So you have to take this distance. So once you mark this distance, right, what you have to do is you have to draw a VSWR circle of that radius what I have specified. So this distance what we are having, right, it is equal to distance which is associated with a rho equal to 4.48 on the VSWR circle. Okay. Now, so we have to mark 4.48. The radius which is corresponding to 4.48. Remember, it is not equal to, the radius is not equal to 4.4 centimeters or something. It is actually associated with the VSWR scale. So you have to measure that and then you have to measure the radius using this VSWR circle. So from 0, what is the distance where 4.48 VSWR is present? So this distance is the radius of the circle, VSWR circle. So on Smith chart, you need to draw this circle. So which is the VSWR circle. So now what happens is this circle, VSWR circle, will be interacting with the horizontal line at 2 points. One is the maximum voltage point and one is the minimum voltage point. So as in the previous session also we had observed which is the minimum and which is the maximum. So this end gives you the maximum voltage point and this end gives you the minimum voltage point. So now in problem here specified that at a distance of 6 centimeters you are obtaining a minima. I know that Vmin is occurring at a distance of 6 centimeter, but I don't know what is the load value. Since I don't know the load value, I don't know where that load is located. So if you just observe this point, right, I cannot traverse from load point to the minima. I cannot traverse in this way. That is load point. This side will be the generator. From load to generator, I cannot traverse. But I know that there is a voltage minima at a distance of 6 centimeter. I know on Smith chart that voltage minima is located at point E. It is located at point E. So now what I have to do is I start from that voltage minima point and move towards the load by a distance of 6 centimeter. So here what I am having, so from point E, I have to move towards the load because this is the Vmin point. I know that Vmin is located at a distance of 6 centimeter from the load. So from Vmin, I have to move towards the load. So if I have to move towards the load, in which direction I should be going? I should be going in the anti-clockwise direction. I should be going in the anti-clockwise direction. So if you get confused, you can refer to this readings which are present. So that is, so here you can see that if you're moving towards the load, you have to move in this direction. You have to move in this direction, and this is the scale what you will be using. So therefore, based on that, what happens is you have to move by how much distance? You have to move by a distance of Zmin divided by lambda. That is, we had represented it as Zmin. So Zmin divided by lambda, which is equal to 0.04. So we have to move a distance of 0.04. So from this is the zero scale, this is the 0. So I have to move a distance of 0.04. So you can, if you just check over here, right, this is 0.04. This is 0.02, 03, 02, 01. This is 0.04. So this is the point where the load is located. But I don't know what is the value. So this point, what you are marking, right? So which is specified as F dash in this case, this point and the center of the Smith chart, that is the center of the VSWR circle. You join these 2 points. So when you join these 2 points, what happens is this line OF dash interacts with the or intersects the VSWR value, VSWR circle at point F, which is noted over here. So this point is nothing but the point which is associated with the load point. Now what you have to do is you have to just read the normalized values. So this point will be associated with one of the resistance circles, and it will be associated with one of the reactance circles. So you need to read that value and try to see what is the value. So that will give you the normalized load value. If you want to denormalize it, multiply that normalized value with Z0, you will get overall value. Now, since again this value is below, it will be negative. So it will be capacitive. So load is capacitive. It's having a reactive component which is capacitive in nature. So this is all for today. Let us meet in the next session wherein we'll be discussing regarding the stub analysis. Okay.